Grading divergent tasks, like university essays, where multiple valid answers exist, presents a structural problem. To understand how human evaluators actually process these open-ended responses, we need to map the hidden logic of the single mark. Most institutions rely on holistic grading. An instructor reads an essay and assigns a single overall mark based on their expertise. It is highly efficient, but it lacks transparency. The student receives a number, leaving them to guess how it was calculated. The alternative is analytic grading. Evaluators break the essay down into explicit multi-criteria matrices. This provides a transparent map of where points were lost, but the rigid structure struggles to capture the complex, interwoven reasoning of a well-crafted argument. Faculty often prefer the intuitive feel of the holistic approach. They know a good paper when they read it. Because the decision happens simultaneously across multiple criteria, the actual rules they use to arrive at that single number fade away, impossible to articulate. The academic community treats these two grading methods as mutually exclusive. By forcing a choice between them, the true pedagogical values driving the faculty's decisions remain locked inside an impenetrable black box. We do not necessarily have to choose between holistic intuition and analytic precision. Researchers at a UK university tested this premise by analyzing over 3,400 essay-based exams across their second and third-year cohorts. They introduced a novel methodology. They asked markers to assign their customary holistic overall grade, but compelled them to simultaneously log silent analytic subscores across 7 distinct criteria. By tethering these detailed analytic inputs to the final holistic output, the researchers built a dataset capable of mathematically reverse engineering exactly what a human evaluator prioritizes when they assign a grade. Before feeding this data to an algorithm, the research team established a baseline by asking the faculty what they believed they were evaluating. The faculty assumed higher-order skills, like critical reflection and argument development, would drive the grade, carrying a 25 to 30% weight. They also assumed cognitive progression. By year 3, they expected these critical thinking criteria to be bumped up further in the grading hierarchy. These stated expectations represent the official instructional goals of the curriculum. They gave the algorithm a clear hypothesis to test against the reality of the grading data. Analyzing this data presents a mathematical roadblock. Standard linear regression fails here because grading criteria like developing an argument and selecting relevant literature overlap heavily with one another. To bypass this, researchers deployed a machine learning algorithm called a random forest. Instead of a single line of best fit, it builds hundreds of separate decision trees, repeatedly splitting the data using binary decisions to minimize prediction error. By averaging the results across 300 trees, the model generates a metric called variable importance. This is a definitive ranking of which criteria most successfully predicted the actual given mark. The random forest quantifies the marker's judgment, providing a mathematical lens into the exact formula the faculty unknowingly followed to decide a student's grade. Comparing expected versus actual data-derived weights for second-year exams inverts faculty expectations. Orange expected weights for critical reflection and argument are high, but green data-derived bars rank them much lower. Basic knowledge and literature recall dominated, accounting for over 50% of true weighting. This third-year exam data tests the assumption of academic progression. Surprisingly, expected progression toward critical thinking did not occur. Data-derived weightings remained static. Advanced students were still primarily rewarded for foundational literature recall, not advanced argumentation. The algorithm proves a distinct disconnect. Explicit priorities published in the syllabus contradict the implicit reward system the faculty apply when grading. This data also dispels the myth of compensatory grading. Faculty are not simply averaging a student's high and low subscores to reach a middle ground number. This decision tree reveals non-linear grading thresholds. At the root node, the primary filter is relevance of literature. This severe gating mechanism means if a student's literature score is below 60, their grade is capped early, making subsequent critical thinking mathematically irrelevant. Holistic grading operates through strict, hidden threshold penalties. These invisible gates prevent students from overcoming foundational errors, regardless of their performance in advanced argumentation. In educational measurement, structural validity is the essential alignment between what a course claims to teach and what its assessments actually measure. When this validity breaks down, it actively damages the learning process. students quickly learn to optimize for the real rules, abandoning the stated goals of the curriculum. You cannot tell students to take intellectual risks and focus on critical thinking, while secretly penalizing them for failing to perfectly regurgitate established literature. An assessment fails its students if the explicit syllabus and implicit grading rules send opposing directives. Treating holistic and analytic rubrics as bitter enemies is a false choice that holds education back. Institutions can adopt a hybrid future. Allowing expert markers to grade holistically preserves the efficiency and intuitive judgment that faculty value. To make this work, institutions must simultaneously log analytic subscores alongside the final number, creating a continuous audit trail of grading behavior. This dual approach acts as an ongoing structural validity check, ensuring over time, curriculum goals continually match actual evaluations. By mathematically mapping our intuition, we can align our grading behavior with our stated goals, ensuring we finally assess exactly what we intend.